Hello everyone. In this video, we are going to cover A3 work for energy. And in this chapter is common to all HL and SL students. We are going to cover basics of energy, work done, conservation of energies, different styles of energies, and also in the cases where it is conserved or not conserved, how can we calculate the energy consumed. So all those things we are going to cover in this particular topic. Okay. So let's start with one important point that whenever there is some kind of a work that has been done by any kind of a force, it will always result in some kind of change in energy. And it can be any energy, any kind of energy, kinetic, potential, different types of energy. But in most of the cases, whenever there is some force is performing some work, it will always cause there is a change in energy. And in this chapter, we are going to first learn how can calculate work done, what is work, and then we are going to cover how the energy changes and how both of these quantities are related. So the first thing, we'll start with the force, uh, constant force, and work done by a constant force. Okay, so a constant force means that we are applying there is some external force that is applied on an object. Yes, object can be experiencing other forces, but when we are considering work done, we try to calculate work done for a particular force, how much the work is done. Yes, other forces are contributing, but how much is that particular one force is doing the work? This is the work done is very force specific. That is the one. It can be net force, but they will specify that F is net. In most of the cases, it can be any particular single force among all the other forces acting on the object. Now, what is work done? How it is defined as? It is defined as it is a product of force applied on the object in the direction of the displacement and the distance traveled by the object. Okay, and it is given by this WFD cos theta, where theta stands for angle between the force and the displacement. So we have to only take the component of the force that is along the direction of displacement. But this is very important part because if the force is perpendicular to the direction of displacement, if the force was like this and the angle becomes 90 degrees, then the cos 90 degrees is 0. Correct? So if the force is like this and the displacement is like this, then in that case work done will be 0. Okay, and if the force is doing work in the opposite direction of the displacement, in that case work done can be negative as well. A work done is measured in joules, that is the units for the energy as well. Okay, it is a scalar quantity, and whenever there is some kind of a constant force, in most of the cases it can be some external force, somebody pushing or pulling an object, or it can be a friction that can also act like a constant force. Okay, what if the force is not constant? In case of variable force, what we need to remember is that they might give us a force versus distance graph. Okay, usually uh, for a variable force, we need to do some advanced mathematics like integration or calculus. But yeah, for simplicity, we will give, if they have given us force versus distance, it can be distance, or it can be, in some cases, it can be extension. Okay, stretching, extension, compression, some unit of meters. Okay, and the force is given in newtons. Okay, so in that case, the area under the curve gives us work done. Then we'll try to revise Hooke's law quickly. The Hooke's law specifies that the force applied by the spring on the object is proportional to the extension of the spring, which is this should be under elastic limits of an object. Okay, Under elastic limit, F is directly proportional to X and F is equal to Kx, where K is the spring constant and it has a unit of Newton per meter. Okay. And if you plot a graph of force versus displacement, in this case, the gradient will be K, that is a spring constant, and if it is extension versus F, the gradient will be 1 by K. Now, we can see that for a spring force, the force changes as per the extension. So if I have a graph of force versus extension, so let's say I want to calculate the work done to extend the spring from 0 to X. Now, according to the previous statement, this should be equal to the area under the curve from 0 to X. So we will specifically take this area. So this area we will calculate, and this area of this triangle is half into base into height. We will get this, and it gives us the energy. This is called as elastic potential energy, half kx square, where x is the extension. So if there is some natural length and then there is an extended length, we can take a subtraction out of it. Now, what if I ask you what will be the work done to extend a spring from x to x by 4? So basically, we are not extending, but rather reducing or compressing it. So what if this was compression? Okay. So from x to x, how much will be the work done? In that case, we need to take the area. Which area we will take? This area. Now, most of the time, what students make mistake is like they take the area directly of half kx square and replace the x with x by 4. In that case, they might get a wrong answer. Okay, so it is always better to rely on the graphs and get accurately calculate the area that is needed. So from x to x by 4, it is this area, not the area like this area. Okay, so to get that, we can subtract the area of a smaller triangle from the area of the bigger triangle, like shown here. And once we do that, we will get 15 by 16 half kx square. So basically 15 by 16 times the original energy when you are extending from. So if this is any kind of a E, then this will be 15 by 16 times E. Okay, so this is elastic potential energy, but most of the time whenever there is an extension related question, I will always suggest, if they have work done related extension related question, always rely on graphs. Try to draw a graph for a given situation, and then it will be easier just to calculate the area under the curve. Then we have another kind of energy for an object in a motion. Kinetic energy, very commonly used. If the object is moving, you will have kinetic energy that is given as half mv square, or it can be also given as p square by 2m, where p is the momentum of an object. Okay. Then we have gravitational potential energy, GPE. Gravitational potential energy is given as mgh, where h is the height from the equilibrium point. So we have to specify that what is h. X is the height, or it can be change in height if in the case where we are calculating change in potential energy. But here height is height of an object with respect to the equilibrium point. Okay. So these are the three main energies that we need to remember: elastic potential energy, kinetic energy, and gravitational potential energy. Once we have done that, then we need to know what is the total mechanical energy. Total mechanical energy is always the sum of total kinetic energy and total potential energy. And this is where the total mechanical energy comes from. The total mechanical energy usually changes, but the kinetic and potential energy uh, changes themselves such that if the total energy wants to stay constant, then if the kinetic energy increases, then potential energy decreases. Like the vice versa things happen. Okay, and whenever this happens, we try to call this condition as conservation of energy. Okay, what is the conservation of energy? Usually in the earlier grade, we learn that conservation of energy is like energy cannot be destroyed nor can be created. It can be only transferred from one form to another. I will try to like make the statement much more applicable is that if there is no resistive forces or external forces, resistive forces means if there is no friction, drag, air resistance, or external forces means somebody pulling or pushing, okay, on an object. So if there is no normal like forces like these, then the total mechanical energy is conserved. This is a very important and big statement. The total mechanical energy is conserved means total mechanical energy won't change if there is no external force or no resistive force. So in that case, the total initial energy, mechanical energy should be equal to total final mechanical energy, and we get the equation that kinetic plus potential energy in the initial part should be equal to kinetic plus potential energy in the final part. So basically, we can choose 2 points, like between this is between any 2 points that we are choosing of the journey of an object. Okay, so this is very important that we have to make a choice about which 2 points we want to conserve the energy. If the conditions are suitable, it will be giving us a very correct value. Okay, and what if there is some kind of external work or some kind of external force or resistive force in the question? In that case, the conservation of energy does not work, because here in the earlier case it was the total energy is zero, where I usually used to write like this, where initial energy is equal to final energy came from. But if there is some kind of external force or a resistive force, then change in total mechanical energy, because there will be some resistive force or external force will change some kind of a mechanical energy, and that mechanical energy change would be equivalent to the work done by the resistive force. So if I drop an object, let's say it has a height of mh, so it will have mgh as the gravitational potential energy, and then if I drop it, what will happen? It will gain kinetic energy. But let's say if the gravitational potential energy is 100 joules and the kinetic energy at the bottom is only 90 joules, it means throughout the journey 10 joules has been lost. Now what is happening to the 10 joules? The 10 joules is actually the work done by the air resistance. Okay. So in this case, the mechanical energy of 100 is converted to 90, and the difference is what is the work done by the air resistance. So this is how we relate the change in energy and the work done. Okay. Another thing that we will, and this is very much important part of this entire chapter. If you understand that if there is some kind of a, if you read a question and if you identify there is some kind of external force or resistive force involved in a question, then always see uh, what is the change in energy, like final minus initial. Okay, always take final minus initial, and then you will get the answer. The next thing is power. What is power? Power is defined as rate of change of energy. Okay, so change of energy, power, change of energy. Now only we learn that change in energy is work done. So this is very straightforward. Power is defined as rate of change of energy, and we can see this is the relationship. It is work done over time also, and its unit is watt. Okay, if the force is constant, this is very important. If the force is constant and we assume that the theta is zero, in this case, the power can be written as work done over time, and work done can be written as force into displacement or distance traveled, and distance over time is velocity. So this will be our power F into V. Now, in most of the cases, we need to remember that this kind of a power is what we call as instantaneous power. Okay, so this power is instantaneous power. At a particular instant, if I give you what is the velocity, then you can calculate power at that particular point. Okay, we will see an example exactly how this power equation comes into play. So in this example, what is happening? There is a car moving at a constant speed at 10 meter per second. There is a weight of the car that is 50 newtons and a coefficient of friction is 0.2. What is the power used by the car to move the car at this speed? So first thing, we need to always draw the free body diagram to understand what are the forces acting. So this is a friction, the normal force, and this is a weight. Okay. So since object is at constant speed, it means acceleration is zero and all the forces are balanced. Now once we understand all the forces are balanced, then the force of engine must be equal to the friction, and the normal force is equal to the weight. Okay. So friction is given as mu times n, that will be 0.2 times 50, that is 10 newtons. Okay, and if we get the force of engine, we can also get the friction. That is because they are both are equal. So in that case, V will be 10 as the constant speed. It is moving at a constant speed. So power generated will be the force due to engine, because we are calculating power used by engine. So that will be equal to 10 into 10, so 100 watts will be our answer. Okay, is that clear? We will see one more example of this. Okay, a car starts from rest and gains some speed at a constant acceleration. So there is a constant acceleration here from the beginning itself. Now resistive forces is 50 newtons and the force due to engine is 100 newtons. Okay, what will be the power used by the engine after 10 seconds of the journey? So first we will consider the what will be the velocity of the object after 10 seconds of journey. In that case, we will understand that the v is equal to u plus at can be also be used in this case. Okay, where the final initial speed is 0 and acceleration is 10, while the time is also given 10 seconds is 10. So we will get our velocity to be 100 meter per second. Now here if I do net force is equal to mass time acceleration, the net force is 50 because 100 newtons is in forward direction, 50 newtons is in backward direction. So net force is 50 and the mass is 5 kg. So acceleration we will get it as 10. Now these are the prerequisite when you are approaching a problem. Knowing this quantity using some other formula is always. Now once we done that, we can calculate the instantaneous energy. Instantaneous power is the force and the velocity. Okay, the force was 100 newton, the velocity was 100, and we got 10,000 watts. But in the case of average power, for average power, we have to take force into average velocity. So for average velocity, I will always divide it by 2 to get average velocity or average value of power. Then the last thing is the efficiency. Efficiency can be written as useful power output over input into 100 or useful energy output over input into 100. Okay, the Sankey diagram. Now whenever there is some kind of efficiency involved, if there is a processes, you can use Sankey diagram to express this processes. Okay, so Sankey diagram is a to a scale a diagram that represents energy transfer or transformations. Okay, so here on the left hand side, if you see that there is an energy input from the left. Okay, so this is like currently at 100%. So all the important divisions are important here. So you can see that this is 1, 2, 4, 4, this is 5, 5, 10, 15, 20. So 20 boxes, small boxes, we can say, or 4 overall boxes, like these 4 boxes are used in a vertical direction. Okay, now once we understand this, then what we need to do is whenever you encounter a wastage of energy, you have to draw the arrow downwards. Okay, while the useful energy output will be given to the right. So we have input, we get useful wasted energy downwards and the useful energy to the right. Okay, so width is important here because width represents the amount of energy. Okay, so if there is too much energy or too much energy is wasted, then we can have a broader downward acting arrow, or if it too less energy is wasted, then we can have a very narrow width diagram downward. So always remember we downward draw in the bottom part all the wasted energy, and the length is has no significance. Like how long you draw it has no significance. How much you draw the width size is that is important. Okay, so this is what is Sankey diagram. The width is decided. For example, how many boxes are there covered here? 1, 2, okay, and 2.5. Let's say. So 2.5 or 2.5 and 0.4. So that much will be the. So here we are considering 50% in the middle. So that will be roughly around 50% is the lost. So this is how we can read the graph as well. Okay. So in this chapter, this is all it is there. Okay. So go through over it once and practice. Thank you so much.